Well, hello. So today we're going to look at section 3.8, quantifiers, right? So this will help us work with propositions involving variables, okay? So we've looked at propositions involving variables before, and propositions over a universe. They're also often called predicates, right? And we're going to basically look at truth values of these propositions. But sort of beyond that, we're going to look at sort of some quantifiers or say operations on these propositions, right? So for propositions, the truth value of the proposition over a universe of truth value of predicates depends on the value of the variable. Okay, so we can see in example 1, we have this proposition or this predicate x is bigger than 3, and that truth value depends on what x is. Okay, so we're asked to figure out what the truth value of 4 when x is 4, and we can see that that's true because 4 is bigger than 3. All right, and we're asked to find the truth value of the proposition when x is 2, and we can see that that's false because 2 is not bigger than 3. Right? So it depends on the value of the variable. We'll see predicates that have more than one variable. So in this case, qxy is the statement that x equals y plus 3. Similar way to find the truth value for particular value of x and y we plug in. So we plug in x is 1, y is 2 into our proposition. We get 1 is 2 plus 3, which is not true. So the truth value of q12 is false. If I'm looking at truth value of q30, plug in x is 3 and y is 0, we get something that's true. Okay? So that's kind of the moral of the story so far, that these predicates that have variables in them, the truth value changes according to the value of the variable. All right, so now we're going to look at the two main quantifiers. We have the existential quantifier and the universal quantifier. Okay, so the existential quantifier says that if Pn is a proposition over a universe U with Tp not the null set, so basically this is that its truth set is not the empty set. So it must be true for at least one value of n in the universe. We say that there exists an n in U such that P of n is true. And this is how it's abbreviated. So the backwards E, it's the statement that means there exists. Okay? And we can specify the universe here as a subscript. So there exists an n in U such that P of n is true. All right? We often drop the subscript universe if it's clear what universe we're looking at, we're investigating. But you'll kind of see it both ways, right? Most often without the subscript. All right, now the universal quantifier, let me leave both up. So if Pn is a proposition over the universe U with its truth set equals the universe, okay, so this means that this proposition is true for all values of n in the universe. It's a tautology. We commonly say that for all n in U, P of n is true. Okay, so again, that's sort of the definition of a tautology, that that proposition is true for any value of n in U. So this is the abbreviation for the universal quantifier, this upside down A, kind of for all. Right? So for all n in U, P of n is true. Okay, and again, we can drop the U if it's clear what we're talking about. First with language, you'll see sort of language of for all n expressed in different ways. So you can see things like all of, for each, given any, for arbitrary, for each, for any. So we'll come across this language in as we're working with these quantifiers. All right, so we are going to come across these in a few problems. So this summarizes when each of these universal and existential quantifiers are true and when they're false. All right, so this statement, this whole statement right here, is true if the proposition Pn is true for every n in the universe. Right? It's going to be false if you can find at least one n for which P of n is false. So it doesn't have to be false for all n in the universe. It has to be false for just one. And this is like a counterexample. All right, now let's look at the existential quantifier. So this whole statement right here, backwards En Pn. So this is true if there is an n for which P of n is true. So if you can find just one value of n, or at least one value of n, for which P of n is true, then this statement is true. Right? And when is it false? So this statement is going to be false if the proposition Pn is false for every single value of n in the universe. So all of them have to be false to make the existential quantifier false. All right, so let's look at a couple of examples finding the truth values of the existential and universal quantifiers. So we're going to look at the proposition Q that says that x is less than 2. Right? So what is the truth value of the quantification? There exists x, so Q of x is true, where the domain consists of all real numbers. So the domain means the universe. So the domain is the same as the universe. All right, so basically I'm looking, like if I look at the existential statement, when it's true, is there is at least one value of the variable in my domain for which this is true, right? And this is definitely the case here, right? I can find, for example, x is equal to 1, which makes this statement true because 1 is less than 2. So this is going to have a true value. Okay. Now, what's the truth value of the quantification? That for all x in the universe, Q of x is true. So basically for all real values of x, this inequality is true. Right? And we can see that this is going to be false. Okay, so because it's the universal quantifier is false if there's at least one n for which the proposition is false, and because I can find a counterexample, basically I can find at least one value of x say x equals 4, such that x less than 2 is false, right? Because 4 is not less than 2, then you say that the universal quantifier here is false. Okay, let's look at the next example. Example 4. So I would say pause the video here and try this out. I'll give yourself 2-3 minutes to find the truth value for each of the quantifications, and then I'll pause, come back, and see what I said. All right, so let's look at this statement right here. So the statement that's given, our proposition is x plus 1 is bigger than x. Okay, so this is an inequality. We can solve it. So subtract x from both sides, and we get 1 is bigger than 0. Okay, we can see that this is always true. All right, so now let's go back to our quantifications. So what is the truth value of the quantification? There exists an x such that P of x is true. Notice that I'm not given a universe, right? So we'll kind of see how it works for different universes. But is there a value of x for which this statement is true? And I say, yeah, there is at least one value of x for which 1 is bigger than 0. Actually, all the values of x makes 1 bigger than 0. So this has a truth value of t. So notice that the universe didn't really matter. So this is going to be true whether our x's are integers or whether they're real numbers or rationals, because it always holds true. All right, now part B, what is the truth value of the quantification? P of x is true for all values of x in the universe. We can see that is also true because this holds true. 1 is bigger than 0 is true no matter what x is. So again, the universe doesn't matter. It doesn't matter whether it's integers or reals or anything else. All right, there we go. As the next example, let's look at these statements. So what is the truth value of this? All right. Okay, so notice you can abbreviate things a little bit. So this right here is your proposition. This is P of x or Q of x, whatever you want to call it. But instead of saying there exists an x such that P of x is true, where P of x is the proposition x squared is bigger than or equal to x, you just put it together. Okay, so whatever is in parentheses here is the proposition that you're investigating. All right, so our domain, our universe, consists of all real numbers. And then let's look at what happens if we change our universe to integers. All right, so is that true that there exists an x such that x squared is bigger than or equal to x? Again, you just need to find one example, right? So x squared is going to be bigger than or equal to x for lots of different values of x. So for example, I could have x equals to 2, and 4 is definitely bigger than or equal to 2. All right, so this statement is true. Right, so again, for the existential, you just need one example for which your proposition is true. So this worked for integers. All right, these are also real numbers. Okay, so it works in both universes. All right, let's look at B. So what is the truth value of the universal quantifier? So if I write this right here, this reads that x squared is bigger than or equal to x for all values of x. All right. So again, let's look at the integers first. Let's say our universe is the integers. And so integers are positive or negative or 0. Okay. So if I have positive integers, let's look at z plus, then the lowest positive integer is a 1, right? So I have 1 is bigger than or equal to 1. And you can see like all the other integers, if x is 2, then I get 4 is bigger than or equal to 2. If x is 3, I get 9 is bigger than or equal to 3, and so on. Okay, so that's okay. You can see the pattern that this is definitely true. Okay, so again, sort of we're kind of going, we're looking at patterns here. You can prove this by induction, right? We've done induction before, but it's sort of often is not necessary because it's sort of this, it's fairly common sense that this will happen. Okay, so let's look at let's say if x is 0, does that still hold true? So when x is 0, we get 0 is bigger than or equal to 0. That still holds true. So all these are true here. This is true. How about for negative? So for negative integers, for z minus. So for negative integers, again, we can sort of start with, let's say x is negative 1. So I get 1 is bigger than or equal to negative 1. So x is negative 2. I get 4 is bigger than or equal to negative 2. These are definitely true because a square is always positive and a negative integer is always negative, so these are also going to hold true. Yeah? So definitely this is true if my universe is all integers. Okay, so for universe of integer, this statement is true. All right, how about if we change our universe and we look at reals? All right, so for real numbers, that means you can have irrational numbers, you can have fractions, and not just integers. Okay, so can we find a counterexample? All of these work, all the integers work, but are there any fractions or irrational numbers for which this will not hold? Okay, so I think we can find a counterexample. Okay, so let's say x equals 1/2. If x equals 1/2, then we have 1/4 bigger than or equal to 1/2, and this is false. Okay, so for any values really between 0 and 1, not inclusive, then this doesn't hold true. So because it doesn't hold true for all values in the universe, then that universal quantifier itself is going to be false. So that's the truth value of that is f for if your universe is reals. But you saw that it is actually true and the universe is integers. Let's look at another example of that kind. Actually, this doesn't ask us to find truth values. It's just asking us what they mean. Okay, so let's look at the first statement. So we're going to copy this down. All right. So this is sort of look like encoded. Okay, so this is the universal quantifier. Okay, so this says for all x values less than 0. So for all negative values of x. And the universe is real numbers. So for all negative real numbers. Right? And the statement in parentheses, or whatever is in parentheses there, that's your proposition. That's your P of x. So for all negative real numbers, so this is looking at your universe right here, how x is defined. X squared is bigger than 0. So the square of the number is positive. Okay, so if you square a negative, then the answer is positive. That's what this says. Okay, you can see that the truth statement of this is it is true, as we know. All right, let's look at the next statement. So for all, let me copy down here. Let's see what this says. Okay, so again we have the universe is all real numbers. So this says for all values of x, there are not 0. So for all non-zero values of y, for all non-zero real numbers, all right, so that's basically my universe. Y cubed is not equal to 0. So this is my proposition. This is my statement right here. So for all non-zero real numbers, the cube of the number is non-zero or not 0. Okay, that makes sense too. All right, let's look at the last statement there. Let's copy this down. Okay, so this one says there exists z bigger than 0. So this is there exists a positive real number. There exists a positive real number, okay, such that, okay, my P is what appears in parentheses, this is my proposition, such that z squared equals to 2. Okay, so that's the translation of that statement. All right, let's pause here.